Landslides, hot rocks, and humans in the southern Pacific Puget Sound, and Andrew Dunning with the Geology News. Welcome to the Geology Hour, brought to you by the Geological Society of the Oregon Country, with assistance from the Portland State Department of Geology and the Beverly Vogt Scholarship Fund. Our panelists today, perhaps for the last time in this configuration, Andrew Dunning, Emma Rahalski, Carrie Gordon, and myself, and Gary Joe Quinn doing our technical direction. Andrew and Emma, I can't say enough about what you've contributed to this project as it's evolved, especially in the past year. Andrew's been with us for 3 years since we started this up during COVID. And Andrew and Emma and Carrie have really helped turn it into something that it was just kind of me hosting for a while. And now it's a panel. And now there's more of a conversational feel to it. And Andrew and Emma have both contributed to that immensely. They're moving on. Both of them have finished their respective master's and undergraduates program. And so we wish them all the success, and we remind them that they're always welcome to drop in, continue to tribute to the Geological Society. And we're really interested in the work that you're proceeding on as you go forward next. So thank you for everything. Here's Andrew Dunning with the Geology News.
Good morning, everybody. Just took a huge bite of my bagel.
Good timing on my part.
All right, this is the Geology News for September of 2023. Starting off with our global earthquakes, our largest earthquake in the last month was a magnitude 7.1 north of Gili in Indonesia. This is an extremely deep focus earthquake, 515 kilometers deep, and that actually reflects an earthquake of the bending of the subducted Australian plate, which is diving underneath the Eurasian plate over here below Indonesia. And as that plate is going down into the earth, it is still pretty cold and rigid, but it bends as it dives down into the earth, and that's where we get earthquakes down at these extreme depths into the interior of the earth. Unfortunately, there was a major earthquake in Morocco, a magnitude 6.8. They don't get those very often, but it is a geologically very active region. This is in the Atlas Mountains here at the north edge of Africa. They are formed by the collision of Africa and Europe. And so you get these thrust fault, these compressional earthquakes here underneath the Atlas Mountains. There are thousands of masonry structures that were destroyed, particularly near the epicenter. I mean, this is a whole village of effectively adobe mud brick buildings that just was leveled by extremely intense shaking right below this location. As of the last report I saw, there were 2,950 plus killed, over 5,500 injured, and again, thousands of mud brick houses destroyed. This is a fairly impoverished region of the world, and there's also a degree of this is just how they build houses over there. And when you don't get a major earthquake for 100 or 200 years, we forget that they happen sometimes, and these are the unfortunate results of that sort of environment. It's very unfortunate. It'll be a long time for Morocco to come back for this, but as always, we wish them the best and hope they are able to recover quickly. Here in the United States, it was a fairly interesting month of earthquakes. We had a magnitude 5 in Northern California near Bernie. This is right here. This is at the very northern edge of the Sierra Nevada mountains, sort of crustal block. So this whole Sierra Nevada mountains acts as a big solid chunk of earth. And we have a strike slip earthquakes up here at the northern edge where this whole block is sliding past other stuff here in the Great Basin and in the Klamath Siskiyou Mountains blocks. So that's kind of cool. That was felt widely around Northern California. And there was also a magnitude 4.5 outside of Wesley right here. This is felt throughout the Central Valley and parts of the Bay Area. Another strike slip compressional earthquake. This is actually a thrust fault related to the greater San Andreas fault system motions. There were also 2 magnitude 4 earthquakes here in southern Colorado, which is unusual and interesting. and also down here in South Texas, which is also unusual and interesting. They get these kinds of earthquakes all the time here in Texas and Oklahoma. Those are where large oil fields are located, so these are related to extraction of gas and oil. But here, this earthquake in southern Colorado looks to me like it could be related to the Rio Grande Rift, which you can actually see on this terrain map quite well. This is the Rio Grande River coming through central New Mexico, and it occupies this sort of geological rift where North America tried to pull apart once and has failed, but continues to produce earthquakes every so often. Global volcanic activity, 29 ongoing or new eruptions. Nothing particularly noteworthy except for Kilauea had a 5-day volcanic eruption, September 11th to 16th, where a fissure opened up in the caldera floor of the Halemaumau crater inside Kilauea caldera. Lava spilled out all over the place. It actually covered the entire, they call it the down-dropped block. In the 2017 Kilauea eruption, the summit caldera actually collapsed further, and the area that used to be a lava lake is now a big, enormous collapsed crater. And it was over 1,000 feet deep, and it has been mostly filled by new lava in the last 6 years. I really think that's cool. This is the third eruption of Kilauea, doing pretty much exactly the same thing of this year. Another one of my favorite volcanoes, Ninoshima, off southern Japan, has been off-gassing and producing steam explosions. This is a very young island. It has only existed for a little over 100 years, and every few years it does a little bit of erupting and makes itself bigger. So Japan is one of those countries in the world that gets a little bit bigger every few years. Very fun. I'm going to start with another oceanic volcano here in Santorini, in Greece, in the Mediterranean. Famous as being perhaps one of the most powerful volcanic eruptions ever observed by humans. This was the Thera or Minoan eruption, 1300 BCE, where the entire part of this volcano, this volcanic island, I should say, exploded and produced an enormous tsunami and destroyed the Minoan civilization and created this big caldera that is now filled with beautiful blue Mediterranean water. This eruption sent tsunamis all across the Mediterranean basin, but mostly to the northward towards Greece proper. Some of these were over 12 meters tall, which is very big. That's obviously a big enough tsunami to cause widespread destruction throughout the Mediterranean basin. And so we want to understand how that works. What are the dynamics of tsunamis in Mediterranean volcano islands? There's a lot of volcanic islands in the Mediterranean, it turns out. So maybe understanding how they behaved at Santorini will help us understand how they behave in the future. So the main question is, are these tsunamis formed from the collapse of the island or from volcanic deposits entering the ocean, landslides, stuff like that? So they found that all around Santorini are these, what they called USBs, or undulating seafloor bed forms. The seafloor has these sort of linear, long, straight, bumpy features. You can see them here in cross-section on the ocean floor, right here. They undulate. And they determined that the way they are shaped, are they convex, concave, or perfectly linear? And that determines basically how they formed. Here, this is the edge of the Santorini caldera. So everything just to the left of this image collapsed downward, kind of like how Crater Lake is. And this is the pre-existing seafloor that has been covered in volcanic deposits. So you get these kind of convex tongues of material you can see on the seafloor. And those are actual volcanic deposits that were thrust out and deposited on the seafloor. That displaces water and causes tsunamis. You also have concave bed forms. This forms from oceanic sediments collapsing downwards because they're heavy, or because it was shaken during earthquakes, or because stuff is getting deposited on top of it. They have found that these pyroclastic deposits were found only to the north of the island, only on the north side. So that's this convex bed form right here. All the others formed after the eruptive period. So this convex bed form is actual volcanic material, a pyroclastic flow that was deposited onto the seafloor, which would have pushed a huge amount of water out of its way as it landed on the seafloor. These other ones are basically at the same time as the eruption, but after all of the volcanic material has been deposited. So this is your ash, your pumice, laying down and settling out onto the seafloor and presumably being shaken by earthquakes during this whole time. So these are also displacing water, but on a slightly different sort of mechanism that makes smaller tsunamis. But they found out that these undersea landslides and these deposits of volcanic materials probably at minimum amplified the tsunami impacts across the Mediterranean Sea. So while the explosion from the volcano definitely moved a lot of water, these pyroclastic flows and volcanic deposits would have amplified that and probably made the tsunamis bigger. This is important for understanding how the volcanic and tectonic hazards of the Mediterranean work. Very important stuff.
Hey, Andrew, I'm just a little curious. You mentioned that geologists who are doing this research knew the size of the waves of this tsunami that happened.
Huh.
How are we able to tell how large waves were from a tsunami? Is it like a deposit? We look at deposits from the tsunami? Or?
Yeah, I didn't look into this, but here in the Northwest and in other places where tsunamis are present, if you look at like mud flats or oceanside marshes, the tsunamis will deposit a thick layer of sand and stuff anytime they hit land. So, if you find if you find tsunami deposits 12 meters above the current sea level, then your tsunami probably went at least that high. And we do see that here in Oregon and some of our coastal marshes. So that's a good guess to how high tsunamis go. There are also archaeological features across the Mediterranean. This is the ancient Greek and ancient Minoan civilizations, where they had buildings near the water, and presumably buildings below 12 meters of this time period are damaged by tsunamis. That's generally how that research process goes.
That makes sense. Thank you.
Yeah. Deep sea carbon cycling. Carbon dioxide is an important part of the Earth's atmospheric chemistry and processes, and obviously it's now probably our greatest and perhaps most interesting existential problem we're facing with climate change. But carbon cycling has been going on for the whole history of the planet. But understanding how carbon and carbon dioxide interacts with the deep sea ocean chemistry, and how does that interact with the carbon dioxide and carbon that exists naturally in the mantle, and how does that get into volcanoes? Carbon dioxide moves everywhere throughout our planet, which is very interesting. Very complicated series of processes. So here, these researchers, part of the International Ocean Drilling Program, which is one of the, I think, one of the most important scientific endeavors going on right now, they went down to the bottom of the Japan Trench, which is 8 kilometers of water, so 25,000 feet to the bottom of this. They took their submarine down there, plopped it on the seafloor, and did sediment cores, over 58 of these sediment cores into the soft mud at the bottom of this oceanic trench. These are the deepest anyone has ever done this. And they found huge amounts of carbon mineralized, so this is calcite mostly, and aragonite, mineralized in these oceanic mud sediments. So during a major earthquake, say, for example, these oceanic trenches are always formed by subduction zones where one oceanic plate is diving beneath another. And this is off the coast of Japan, so they get major subduction zone earthquakes every so often. And so they found these layers of extremely high carbon content in the deep sea mud. So they thought, okay, maybe this is a paleoseismic record. This is a record of past earthquakes. Every time you get a major earthquake, it sends up a tsunami onto Japan, and it drags a whole bunch of plant matter and other things down to the bottom of the ocean. So that introduces a bunch of carbon to the deep sea chemistry zone, I guess. And this mineralizes over time because it has to do that. That's how chemistry works at the bottom of the sea. I'm not an oceanic geochemist. But over time, this mineralizes and gets buried by more mud. So you get these carbon-rich layers, and you get this non-carbon-rich layer. And then you get a carbon-rich layer and a non-carbon-rich layer. And over time, this turns to minerals like aragonite calcite and some others, and that gets compressed. And then it gets taken by this oceanic plate. It gets carried on the Pacific plate like a conveyor belt and gets subducted underneath Japan and ends up in the mantle. So this is how carbon moves between the crust and the atmosphere and Earth's interior. So this is the first time this has been directly observed and is very important and unprecedented way of understanding how carbon interacts with our deep sea environment. Pretty complicated, but very important and interesting.
Andrew, I've got a question from
Yes.
Paul over here.
Andrew, what kind of submarine allows you to take cores from 25,000 feet down? Is it remotely operated?
Presumably remotely operated. I guess they could have done this with a... Okay, I don't know why I didn't think of this. They could have done this with what's called a piston core, which is a big metal pipe with basically a big weight on the top of it. You drop that off the side of your boat, it plummets down to the ocean floor. Your pipe lands on the ocean floor, then the weight comes down and hammers it into the soft mud. So that gets you, I don't know, hard to tell because these are pretty small. These core samples have been cut up already. You get 5-10 meters of mud that you then get to pull up and analyze in your boat lab.
Fascinating.
Yeah, very cool.
Also have a question from Carrie.
Yeah, quick question here. So this is earthquake related. It would some of this carbon be bound up in turbidites, which for folks that don't know what that term means, it's an underwater landslide. So would you see something like that connected with turbidite sequences, like in the Coast Range, the Tyee Formation?
Yes, absolutely.
Okay.
And those do contain lots of carbon because they are mostly made up of turbiginous sediment. I mean, sediment that is derived from a continent that includes plant matter, organic debris.
So Andrew, did you find when looking into this topic that these carbon-rich layers tend to be concentrated like near a continent or near a landmass, and we don't see these like in deep sea sediments farther away? So this carbon cycling really only happens like on active margins or around, I guess it would have to be on active margins if subduction plays a role in it.
So this kind of carbon cycling does happen in the ocean, but these sort of thick layers related presumably to the earthquakes was something that hadn't really been considered in climate or carbon cycling models before. So oftentimes in this whole carbon cycling field, they end up stumbling across new ways carbon is being cycled in sort of novel places. Like in this case, it's at the very deepest reaches of the ocean right next to Japan, where just stuff is getting dumped into this oceanic trench every so often. Up here, we're doing research on one of the other graduate students at PSU is doing her thesis on the amount of carbon trapped by the Mount St. Helens eruption and landslide. In all these old growth trees that then got buried by landslides, how much carbon is stored in there. So carbon cycling is basically trying to figure out all of the very different ways that carbon dioxide is trapped inside the earth. Did that answer your question?
It did, yeah. Thank you for clearing that up for me.
Okay, good. I'm going to move on then to the Great Oxidation Event. The Great Oxidation Event is one of the most important events in Earth history, about 2.4 billion years ago. And this is when oxygen really first became concentrated in our atmosphere, allowing multicellular life to form. So oxygen is cycled much in the same way carbon is cycled through sedimentation in the ocean, erosion of uplifted rocks, ocean chemistry and atmospheric chemistry, and the biosphere. So these researchers took samples of zircon that contained inclusions of the mineral apatite, and they threw them into a synchrotron, which I guess is apparently a kind of particle accelerator. They collected these from Brazil and elsewhere in South America, of these very old 2.5 billion year old rocks. And they analyzed these apatite inclusions. They specifically did the inclusions and not the zircons, because the zircon is a very hard, very robust mineral. It survives getting sent down into the middle of the earth and then brought back up. So these rocks, these mineral grains have probably been recycled several times, preserving this 2.5 billion year old apatite inside. And looking at this apatite, they analyzed how sulfur exists in this system. They looked at what's called its oxidation state, which is basically how its electrons are being used to interact with other atoms in the crystal structure. So these crystals originally formed in subduction zones 2.5 billion years ago from subducted 2.5 billion year old sediments that reflect the state of ocean sediment at the time of the Great Oxidation event. The amount of oxygen available in these subducted sediments in things like limestone and dolomite, other oxygen and carbon-bearing rocks that end up subducted, that reflects or affects instead the amount of oxygen that is present in magma derived from those subducted rocks. And that gets crystallized and preserved in zircon. So this has been preserving an actual apatite mineral inclusion from magma of Great Oxidation Event era rocks. It's a really complicated way of getting from 2.5 billion year old atmosphere to 2.5 billion year old magmatic crystals. But this was sort of a proof of concept. This had never been done before, for figuring out how much oxygen was available and how is that getting cycled between the atmosphere and the mantle, the interior of the Earth, which is really important for understanding how our, what mechanisms are driving changing atmospheric conditions over geologic history. That's all I've got for this month. Wanted to leave plenty of time for our upcoming lecturer. I'll see you next time I see you. Thank you very much for listening.
Andrew, I'm sad that we won't have your wonderful blend of earthquakes, volcanoes, and research that we've had for the past 3 years now. And I hope that you continue to go on with the great work that you do on your video channel and compete with us and surpass us and continue to do the great outreach that you've been doing. So again, thank you. Julian has an explanation of what a synchrotron is in the chat.
Oh, thank you.
It's available. All right. Well, Kate, if you are ready. Kate, I met at the Archaeological Roadshow several months ago. And because her work crosses over concern about Native American presence in the Pacific Northwest with the archaeological methods issues and the geology of the Osceola landslide, well, I'll let her explain it. It's a really rich topic. And Kate, thanks for joining us today.
All right. Hello, everyone. My name is Kate Shantry, and I am currently a PhD candidate at Washington State University. I'm on the Vancouver, Washington campus. I've also been a professional archaeologist working in the Northwest since 2001. So I'm kind of a later PhD student, and I'm, applying a lot of that real world experience to my study here. The title is Dropping into the Valley, Landslides, Hot Rocks, and Humans in Southern Puget Sound. And I want to thank Paul for inviting me, and thank you all for your interest. And since you mentioned the roadshow, this is my shameless plug. There's going to be a fall archaeology roadshow in the Dalles, November 18th, and it's a free event. And we also are looking for exhibitors. So if you're interested in that, it's happening. All right. So the overview, I'm going to kind of guide you through what I'm going to talk about, and then I'll talk about it. So first, in the background of this, those are what I call boiling stones. They are rocks that have been heated and then cooled very quickly, like heated and cooled in cold water. So they've experienced what's called thermal shock. And so I'm going to get to that at the end, and I'm going to preface this. These are created by humans, and the humans that created them are people from the Northwest Coast. And so I'm going to talk a little bit about how the understanding of the world works in that context for Indigenous folks in the Northwest in the present and the past. And then I'll be talking about human and environment relationships, because you can't really talk about Northwest Coast archaeology without incorporating both, because there really is no line between them as we're kind of learning that as we're looking at larger landscapes and things. And one of the things that demonstrates that are traditional practices. So when we have older archaeological material, but there's a link in the way people are doing things and the materials they're using that shows cultural continuity. And so to that end, my dissertation research has involved looking at hot rocks and trying to develop some attributes that are macroscopic, that people out in the field can identify instead of just a fire-cracked rock, because these rocks are very bulky. These are ubiquitous items on the Northwest Coast. They don't get collected a lot, and they don't get curated a lot because there's cost and space issues with that. And there's, sampling usually is related to something having to do with a fire feature. So I will get more into that. And then, I'm going to go back to those intersections between the cultural and the natural, because in both my academic and professional work, actually my professional work, those things have come together actually a lot easier than, say, in academic context, because there's a lot of, different professionals working on the same project. So with that, I will get into it. So my study area is Southern Puget Sound. This is a historic photo and a modern photo of Alki Beach, which is in West Seattle. In the top there, this is a, canoes in an encampment in Seattle about 1910. I think that picture is from the Mohi Museum of History and Industry in Seattle. The photo on the right is canoes that have been just come ashore at the Tribal Journey, which is an event that happens every year where Northwest tribal people will canoe to a home location. And this year, the journey, the final destination was at Alki Beach, and was hosted by the Muckleshoot Indian tribe. So I have a quote there from Virginia Cross from Muckleshoot that says, "The land is tied to our heritage. The land means something to us. It's where we live. It's where we are going to stay. It's where we'll always be." So I think these two pictures sort of demonstrate, that's more than 100 years between those. All right, so this cultural area, as far as archaeology is concerned, the larger map is the Northwest Coast, which you can see, all of British Columbia, a little tip of Southeast Alaska, and then Oregon, and right into Northern California. Humboldt Bay is the southern extent, and that's a cultural grouping based on cultural traits, language, kinship, those things. And on the right is a map of the Salish Sea, which is really useful. And we've only had that as a geographical entity since about, I think, 2000 or something. Before, there was always Canada and Washington. But now, we look at it as the entire sort of Salish Sea area, which is also useful when you're trying to connect different archaeology over different places, because archaeology can be done a lot of different ways. And Canada and the US have different histories of doing archaeology. This is another map showing the Salish Sea and then the language territories of the different folks in this area. I just need to move you all over. Sorry, just a second. I can't see part of this. But you can see, all the tribal designations. And so in the area that I'm working, it's concerned with Muckleshoot, the Puyallup Indian tribe, the Duwamish tribe, the Tulalip tribes, Snoqualmie tribe, and the Suquamish tribe. Those are all folks that have ancestral territory in my study area. So this is a map highlighting the language area of Lachute Seed, which is, we use the term Salish, but Salishan is actually a language that was used in the Columbia area, but it kind of stuck. So the Puget Sound Salish folks speak Southern Lachute Seed, which is a dialect. And you can see that in relationship, to Oregon and British Columbia. And then also you can see all the waterways and sort of, it's a very unique inland sea in this particular area that influences the kind of archaeology that we're looking at. And so here I have some different study areas as far as the work that's been done archaeologically. Seattle is in the wrong spot if you're really looking. It should be one to the south there. But this is the area that I'm working on. So this is the older shoreline and these foothills. And this is the Gulf of Georgia. This is a very well-studied area archaeologically. Fraser Delta is also a very well-studied area. And that's strictly in Canada. And there's several universities in Vancouver area in BC that have done decades and decades of work. Olympic Peninsula, if you're familiar with the Ozette site, that was a very unique and good partnership between Washington State University archaeologists and the Makah tribe. And then we have Vancouver Island over here. So these are kind of like the sub-regions of archaeological work in that area. All right, so I'm going to be talking about Mount Rainier, and Mount Rainier, its more traditional name is Tahoma, and that has a Lachute Seed spelling as well that I don't have here, but this is a native artist drew this, and it was included in a news article because the Puyallup tribe is trying to get the name of Mount Rainier changed back to its more traditional name. So that's what this image is about. And you can see that these are whale fins and Rainier in the background, which has to do with the setting of what I'm going to be talking about archaeologically. And then as far as finding archaeological sites in this area, deep time. For Madonna Moss, an archaeologist from University of Oregon, let's see, a few years ago, no, more over 10 years ago, wrote a book that's called Northwest Coast Archaeology, and focusing on the depth and, what we trying to get at the Middle Holocene, that older record, because the existing shorelines, where you can see archaeology like shell middens, which are calcium carbonate, organic soil, and a lot of those fire-cracked rocks all kind of mixed together, and because of erosion and on the shoreline, sometimes they're exposed. So if you were doing a survey in a boat, it would be easy to spot those, but they tend to be only 1,000 to 2,000 years old, because older shorelines are buried, as the gentleman was talking about in the news. It was a good setup to kind of explain that. So getting at this deeper archaeology was one of my goals. So here we have Mount Rainier. That's a photo that I took on a hike somewhere. And then we have the Puyallup Delta. So how I first got interested in this was I was monitoring a salmon restoration project on Hylebos Creek, which is on the northwest part of the Puyallup Delta, which is in Commencement Bay and is now the Port of Tacoma. So if you were to drive on I-5, it would just be concrete in the Tacoma Dome, and you wouldn't really notice because the Puyallup River has been channeled there. There's been a lot of modification. And so I was working down there, and I was working with a couple of geoarchaeologists, Charlie Hodges and Brandy Rink, who were coworkers of mine at the time. And we ended up identifying a buried site, and we had to evaluate it, and we used sonic core drilling in order to do that. So sonic core will vibrate down into the ground and pull up the dirt so you get it in sequence rather than if you were just drilling down, taking a sample, drilling down. You know, they're destroying everything while they're drilling, right? So we wanted to get the whole sequence. So when the geoarchaeologists were doing the work of reconstructing the delta, they were identifying these volcanic sediments with an origin from Mount Rainier. And so I'm not a geologist, I'm an archaeologist. So it's taken me about 20 years of my career to be able to look at a landscape and try to, you know, visualize how it was in the past, because it's a very dynamic landscape here in Puget Sound. I have this here because I wanted to talk a little bit about Indigenous ontologies as far as understanding of how the world works. There are what are called changer stories. So when something happens, you know, like I would call it a cataclysmic landslide, it might be more seen as a transformation. And there exist oral stories that have been written down, you know, in modern times, but they reflect these events. And there is one that is called How the Whales Reach the Sea. And there's 5 versions of this legend in Arthur Ballard's book. And Arthur Ballard was a local ethnographer in the area who grew up with, you know, tribal folks in kind of settler times. And it talks about how the whales got stuck. You know, the valley was all salt water, and then this landslide happened. The whales got stuck inside, and eventually they burrowed their way back out to the sea. And so the burrowing back to the sea reflects the river down cutting after this Lahar event that I'm going to talk to you about. But before we get to the geology, there's more information about traditional practices, because me looking at the hot rocks reflects some things that don't preserve in the archaeological record, but really reflect, you know, cultural traditions on the Northwest coast. And that's why I'm really interested in the hot rock data, because it's a proxy for these container technology. And this is a picture of a mat house, which is a summer living setup with baskets around it. And that's tightly coiled baskets were used as containers for water and boiling. This is a museum photo and a historic photo of a couple on the beach that are weaving. And this is an example of you could see how you could hold water in that. It's coated with a resin, so the stones are heated separately. The water is put, you know, in the container, and then the stones are transferred into the container. And that is when they get that thermal shock that causes what I'm now recognizing as a specific morphology that we can recognize when we're out in the field. Here's another, this is a Yakima basket that was at the Washington State Museum of Anthropology in Pullman. It shows that tightly coiled technique. Some of the boiling baskets have a wider bottom, and they're called kettle baskets. So I'll show you that in a minute, but this is a close-up of the inside of that basket. So it's meant to be watertight. There's other baskets, you know, for other things like shellfishing that are, you know, have a much more open drainage characteristic to them. So a graduate student up in University of Victoria did a did some experimental work with what are called bentwood boxes, which is what you're looking at now. So this sort of shows you the process of how the rocks were transferred into the water. And so the bentwood box is a specific diagnostic technology used only in the Northwest coast, or only found here. And you would take, the people who would make these would take a cedar plank and steam it using hot rocks, so a different use of hot rocks, and soften the wood and then bend it. So you would have 3 corners, and then the last piece was sewn on and the bottom was sewn on. So if I can identify boiling stones out in the field, then I can start talking about activities that might include bentwood boxes and baskets, which I call boiling technology or container technology. So these are some images of some folks actually constructing the bentwood box. So you can see that, because generally when we're looking at hot rocks and talking about hot rocks, food is the first thing that comes to mind. And that's also because most of the sampled hot rocks come from, a burnt earth, oxidized area with, some faunal material or bone preserved in it. And that would also be useful for radiocarbon dating. So the focus has tended to be on those contexts. However, the rocks that are being used, once they're exhausted, they get discarded in secondary contexts or moved away from where they were originally used. That's what we call a secondary context. Technically it would be discarded or exhausted material. And then there's sweat lodges, which is another activity that we don't usually see a big archaeological signature for. When things are made of perishable materials, and when they're not, they're in acidic soils, which the upland environment is full of acidic soils, we don't get a lot of preservation of anything but stone. And that complicates the interpretation, especially when we're trying to link things to this great record we have on the coast that has all of this, faunal material, fish bone, shellfish, things people made out of all these items, get preserved in that calcium carbonate conditions that we don't have in the foothill areas where I'm looking. This is another traditional activity of steaming a canoe. And so these are a couple of Chinook folks that have the expertise to, this is a practice that people would do because there isn't a separation between like the animal world and the human world in this understanding ontology. So, the canoe is getting a send-off, or a coming out sort of celebration, getting prepared for its journey. So the different size of rocks. So when I'm looking at this, I'm thinking, okay, so those are bigger rocks that maybe you wouldn't use if you're transferring with a tong, because I'm thinking of the other uses, because all I'm going to find when I'm looking, in the ground are broken rocks. I'm not going to have a canoe or a note that says this is where we steam the canoe. So this is an example of an earth oven, which is another context where you find slow and fast cooled hot rocks. It depends. They can tend to have multiple uses, and then they're cleaned out. So they can be a little bit hard to pinpoint, one discrete function unless it's, used only for camas in a camas oven or, something like that. So this is me early in my career. I started at the University of Washington as a cultural anthropologist. I went to Alaska my junior year, learned about archaeology, and I've been doing it ever since. In 2005, I got a master's degree at Western Washington University. I was working with Dr. Sarah Campbell, and I had taken a job and just been a worker on this job that was excavating the features that you're looking at now. And so when there's a big excavation, you need a lot of bodies to help move the dirt, right? So I got hired because I had gone to Alaska and I did a field school. And so I was trying to, for my master's thesis, I was trying to understand the difference, between compare and classify features and look for attributes that could apply so we even could compare them, because there was a tendency to only describe them and not put them in comparable units, because as you can see visually, that, you know, they're pretty different. But calcined salmon bone was the primary faunal material in all of these features, or almost all of them. But I was dissatisfied with what I could learn, because I didn't have the hot rocks that were associated with this. I didn't design the study. I was just a worker, and it became my thesis later. So I got obsessed with these hot rocks. And as I did that, you know, I've come to learn that you can get residue off hot rocks, and, you know, other lithic materials. And that's mostly focused on protein residue, and lipids, which are fatty acids, which can get to, you know, your mammals and your seafood. As far as plants, it's a lot more nuanced, because there's, you know, thousands and thousands of plants, and native folks use probably all of them, you know, in some combination. And then we're getting some combination in this feature. But there are ways to do it, which I don't have time to explain now, but this is just showing some of the different things. So that's another way that the hot rocks have information related to what people were doing, and rather than just, oh, this is a fire cracked rock. But that's not a macroscopic thing. These are just a couple fancy photos. The bentwood boxes were also used for storage. So there's decorated ones, there's more utilitarian ones. The only time I've never found anything related to a bentwood box. Fragments of woven material I've found in some wet site conditions. Here's a couple photos that from Franz Boas, famous Smithsonian ethnographer who came out here and worked with indigenous people on language. And so these are photos of, he called them kettle baskets, and you can see the wide bottom there. So for my study, I wanted to do a typical study of basic hypothesis. Well, what's the best rock for boiling? Because I know, growing up in Puget Sound, it's not just one rock, like when you're in the California and it's all sandstone. There's all kinds of different rocks on the beach, as I'm sure all of you know. So I selected ones that look similar to things I've seen when I've been on digs. And I was at WSU, so geologist John Wolfe over in Pullman helped me. I wanted an official ID before I said, you know, this type of rock is more resistant than the other. And you can this is kind of an early morning shot of Mission Beach, where I collected some of the experimental samples. So here, the study was that I heated the rock for 600 degrees Celsius for an hour, and then I put it in water, and it boiled for about 5 minutes. And then if it didn't break, I continued to do it. And so these 4 work the best of all the specimens that I tried. And I divided them fine grain, coarse grain, but it didn't really make a difference because there was crossover. So there's basaltic andesite, granite, diorite, and I think another basalt. We'll see if this passes the expert geologist test. So after I figured out which material types, you know, were the strongest, and it pretty much basalt is the way to go. There's reasons why quartzite are not good for boiling stones that you probably already can guess, but they fracture into a lot of pieces because they're silica. So quartzite's nice and smooth and round, can heat it really high, but you don't want to be using it for a boiling stone. So the next study I did was I took the rocks that I collected, I sliced them in half with a tile saw. I was working with the School of the Environment at Washington State. And I sent I cooked one half and the other I didn't. And then I had thin sections made of each. And so these are the before and after. The before is the thin section of the unheated rock, and the after is the boiling stone that I heated. And so what I discovered, which in the news he was explaining it quite well, is that when that energy from the thermal shock occurs, it has to go somewhere, but when it hits these minerals, it can't get through them because they haven't been heated to their melting point yet. And so this kind of redirects. And so you get this intersecting fractures, which I think is a characteristic. And it makes these planar surfaces, which I'll show you, but I'll just, I'm not sure if these are in order. This is this specimen, this basaltic andesite. So if you look at this, I also noticed that it was outlining the grain contacts a little bit. I'm just brushing up on mineralogy as a what I need to know basis, which is not a good way to do it. But sometimes as archaeologists, we don't have time to take every geology class. And these were imaged at the Peter Hooper School of the Environment. There's a tephra analysis lab there that Nick Foyt and Scott Burrows operate. And so Scott Burrows helped me with this, which was nice because normally it would cost. So here's the diorite. And so this was my most coarse grain. This is the one that was kind of surprising because the basalt made sense, basaltic andesite. But this one wouldn't be used for anything else like flake stone to make, sharp edges for other activities. Okay. All right. So these are stones I actually picked up on the beach in front of an eroding Sheldman archaeological site. And so this is what I'm talking about, that morphology that you want to recognize in the field. So then when someone takes their notes, they can say X boiling stones and then other fire-cracked rock, because it's a little harder to pinpoint the morphologies of slow-cooled rock without the heating facility. But as far as what to note down in a systematic way, I noticed these planar surfaces. So counting these planar surfaces, I think, is something that I've started doing in my analysis. And so I'm going to quickly tell you about another thing I discovered in my work that relates to quartzite, because one of the things people always want to know is how hot was the rock heated? They want to know the temperature of the rocks to figure out what kind of activity, I guess. And without archaeomagnetism, or I think that is the technique that one uses, which would involve a research design and a plan and a sample and probably not be appropriate for every project. I was looking for something that would tell a temperature threshold. And I was in a ceramics class and studying stone temper, and it got me onto this quartzite where I learned that there's these irreversible changes in the polymorph. So it goes from quartz to, I think it's tridymite to cristobalite are the different textures that you can recognize visibly. So these are some of my experimental rocks, just from throwing it in the fire, waiting until it was glowing orange, and these are different stages of it. I found that studies on concrete were also, studies on concrete were also useful. And I think for me, I think that these make a lot of sense in sweat rock context, where you'd be pouring the water over the rocks rather than putting the rock in the water. So I don't know if you'd have the same, spall situation, which wouldn't be good if you were in a sweat, but you would understand how to use these materials, obviously, if you use them every day. But in the Arctic, I did work up in Kotzebue on one project, and we did notice these rocks that had an outside texture that sort of looked like tooth enamel. And that wasn't what we were there for, so we didn't collect them or look into it. But I was thinking, oh, well, if you were in the Arctic, quartz is going to keep you warm the longest, because it has the highest temperature threshold, or a very high temperature threshold. So that's kind of a question I have out there. And so you're probably wondering, okay, well, how does all this hot rock stuff relate to the mud flow? It relates to the mud flow because we don't have good preservation where the mud flow deposit is. The mudflow deposit is on the Enumclaw Plateau. The lahar came down. There was a couple of, I think, eruptions on Rainier, and there was a collapse, and the sediment came down, and then it kind of blanketed out on the flatter landscape of Enumclaw Plateau. And at that time, the shoreline was right there in Auburn. And so back to when I was looking at the Puyallup Delta and talking about those volcanic sands down in Tacoma, you know, that's part of the progression of this material over a few thousand years. Because the lahar, the Osceola mudflow, has been dated to 5,700 calibrated BP. So we have that date, which is great because as archaeologists, you know, we're not finding a lot of charcoal up there. But the problem is we used hand excavation techniques to identify sites. And it's a very thick deposit. And so normally we would not dig past a glacial surface if I was on an outwash plain. But in that area, we just can't get through the mud flow by hand digging. So that's kind of the surface that we terminate our search as far as subsurface. And then I've been using monitoring well data from the Department of Ecology to see if, I can identify where they're describing this lahar. And another reason why the hot rocks relate to this area is because there were very large anthropogenic prairies in Enumclaw. And I'm not sure how that relates to the lahar, but if a lahar came down and cleared a bunch of land, and then people wanted to keep a nice open area with all their favorite plants and encourage deer and elk to come, that's sort of the theory. There's a very rich cultural record post mud flow in the area of the Muckleshoot Indian Reservation and that entire landscape. So I'll just leave that there and try to fill your questions. Then I have a Jimi Hendrix picture here because in the song, Jimi Hendrix is from Renton, Washington. And so he lived in this landscape and he wrote this song called Voodoo Child. And the opening lyrics are talking about chopping down a mountain with the edge of your hand. And I'm a music person. And to me, that just had a connection to the mud flow and lahar. So this is why I have a picture of local son, Jimi Hendrix. And I hope that made sense.
Hey, we're so lucky to have you. Thank you. That was brilliant and fascinating, and I am looking forward to the questions. So let's keep the recording going for a little bit. We have reached our hour, so if you came for the geology hour, you're free to go, but also you're free to stay and ask questions. And Carrie, I'll let you navigate the questions.
Well, I have one question before we take other people's questions. So after your research, it seems like maybe there's like two things that you can look at macroscopically to identify these hot stones, like these kind of cracks. And then you also mentioned some kind of like deposit, like maybe like a waxy deposit. So what do you mainly look for in the field to tell like this is a hot stone versus some other kind of like collection of stones in the field?
That's a good question. And I've been asked that question many times by archaeologists who don't want to decide for themselves. It's really the morphology of it. There's crenulated edges, which, I mean, these are not words that we usually learn in archaeology. So I've whenever I learn something about geology, I really want to make sure I'm using the term correctly, because we don't want to just, sometimes, we use the word possible a lot, it's a possible this, but it does have a distinctive morphology, where it's kind of, I always describe the rocks as like twisted up, or, like if you go out and it's really cold and you kind of tighten up and shiver, right? The rocks sort of have this like twisted kind of morphology on them. And then the material type, so I'd be looking for basalt or basaltic andesite. I wouldn't, the slow cooled rocks have a very, granite or something exfoliates, so it's hard to even collect or anything like that. yeah, it's kind of a combination of things, but and that it's different from all the other rocks, right? Because that's what, as archaeologists, like, is it cultural or is it natural when we're looking at a piece of stone trying to figure out, did nature do this? Is this some water spot, or did someone grind this, purposefully? And so, a uniform size, the distribution, sometimes you can, if you're getting a particular distribution, if there's flake stone, that's always nice, because usually you'll get those in combination, just because lithics are what's out there. Did that help?
Yeah, no, that did answer my question. It was a really fascinating presentation.
Oh, I do know, actually, I remembered one thing from a study. I'm learning that the ratio of spalls to larger pieces might be important, because we don't usually, spalls are kind of small, and off the top of your head, you wouldn't think you could learn anything from them, right? So we tend not to collect smaller than a certain size if you're in a rush and not doing a research project, right? But there's a difference. I noticed that there's a difference. I got to analyze some hot rock from different features. So I knew they were from, burned earth context at a fishing location. And they had a lot of macrobotanical elderberry in the area. And so I've since understood from looking at the traditional and the botanical stuff, since elderberry has to be, the stems can be toxic, you either have to remove them by hand, or I think boiling a little bit would actually reduce the toxicity. So that's kind of, not something that you would normally think of as a use for boiling stones in like the preparation, even though they're probably not cooking elderberry all the way. It's more of a medicinal, I don't even know. There's probably tons of uses for elderberry, honestly. I don't know, but
Yeah,
so the ratio of spalls to larger pieces, and a consistent morphology, I think would help and be convincing.
yeah, this is fascinating. I mean, I didn't even know that these were that these existed. So, it's gonna kind of have a new light when I'm looking at like a collection of rocks that are all kind of in a pile in the same.
Well, I've been fooled though, because the wetting and cooling, the natural wetting and cooling can fool people, because they do, they're still going to crack where there's weaknesses, whether it's, a natural or cultural, I don't know, event that makes it crack, I would think.
Paul, you had a question, and then I've got one.
Okay, Kate, I'm really impressed by folks like you who are working at the intersection of these cultural ontologies, which have a political dimension. I mean, there's a lot at stake for Native tribes in the way that stories are told. And I'm curious what, as you've worked with different ontologies, what as a professional, kind of what wisdom you have to impart about how to approach that material and build those relationships.
Well, I think, your work should speak for itself, whether you're doing ethical, work that is inclusive. I think that's important. The landscape has definitely changed. And I would say my professional career is what's helped me the most, because I would have constant, interaction with people, and people would be reviewing my work. I would see them in the field if they would come visit. I worked for a consulting company out of Seattle for 10 years. So I was, seeing the same people. And I had started as a young professional I didn't even know, but I got in with a really good company, and all of those people are doing good things now. The chairman of the Suquamish tribe, Leonard Forsman, worked at the company I got hired as. Dennis Luark, who is the archaeologist. There was a person at the Department of Archaeology and Historic Preservation, and another person is the archaeologist for the Muckleshoot tribe. So it's relationship building. And I think not always visiting when you have an ask, you don't just contact or be a part of the community when you need something. You know, and doing your homework so you understand. If you, you know, through my work, you know, we have to, it's suggested that we include a section in our consultant reports about ethnographic background. But I've come to learn that just citing the one white person in settler that decided what all these things were called is insufficient, you know, for that. And it doesn't really help the archaeology at all anyway. It's just, you know, you have to, we've tended to lean on the ethnographic record a little bit too much instead of letting the questions actually come from the people themselves. And so now there's a lot of partnerships because archaeologists, you know, my mentors have been involved. My advisor is Dr. Colin Greer. He works with the Penelakut people, the Lyaxan people. He's worked with them for over 20 years since the time of his dissertation. So I've kind of chosen my mentors because that's important to me. You know, that's just part of the work that has to be done. And I grew up, you know, in the Puget Sound. So I think you're a little more exposed to kind of maybe Native issues or just Native presence.
Thank you.
Okay. So Kate, I've got an observation and then a question for you, but having worked 40 years for a federal agency, I spent a lot of time with archaeologists as a geologist because they'd have a lot of questions. Where's the quarry for this material? But more importantly, working on fires and working around recreation and fire rings, that gives you an opportunity to see how rocks behave with heat and different rocks. And that's just me as a geologist. I'm going, oh, hey, that one cracked a lot. And that was just from campfires. So I really appreciated what you saw with the thin sections, because that confirmed some of what I have observed over the years. So it's, have you worked with colleagues in other geologic environments like the Southwest to see if they're finding similar relationships with the rock use, with heating, with baskets? I know the Pacific Northwest is big with the woven baskets, but what about some of the other areas?
Well, the connection, because this hasn't had a great deal of study archaeologically on just the rock mechanics and properties, you know, but Randall Schalk is the archaeologist who was an early boss of mine, and just his name sort of came up in things I was supposed to be citing, you know, in my background research. And so he was the one who, I think there was some work done in the Chester Morris Lake area in the late 70s when the Forest Service and the parks were doing more large scale surveys to kind of inventory what they had, you know. And so he sort of identified that fast, cool, slow, cooled, that there was something there. And then an archaeologist named Alston Toms, who was at WSU with Randall, he ended up teaching at Texas A&M. And so he has tons of students. He passed away a couple of years ago, but they were working on agave pits. They had all these agave pits. So boiling stones wasn't the main interest, but these students were doing a bunch of experiments also with clay balls for heating elements and those kinds of things. So and the folks that are interested in this, we're just now getting an interest group with the Society for American Archaeology. And so people are getting more interested, especially because we can do more things microscopically too. So
excellent talk, thank you.